Hey everybody, welcome to another Avalanche Developer Community Call. As always, we are joined by some amazing engineers. This week, Aaron is actually at Blockchain Week in Korea, so he won't be joining us. So instead, we have Joshua Kim joining us. Thanks for joining us, Josh. And then, of course, we have Stephen and Patrick, as always. So this week, we got some really cool topics: Cortina 9, new Avalanche-rs library and SDK, and then, of course, the Hyper SDK block pruning. So with that, I shall now hand it over to Pug. Gentlemen.
Great. Thanks, Gabriel. Good to see everybody again. Let's first cover, I think, what we released last week or 2 weeks ago with Cortina 9. Cortina 10 is right around the corner, but we may tease a few things there, but we'll go first into Cortina 9. And I just got my local Explorer demo up, so I will be able to tease the DevNet a bit towards the end of this. But yeah, can we share my? There we go. Perfect. All right, Stephen, you want to take the lead here?
Yeah. So the namesake of Cortina 9 is the Z standard compression. So we've actually supported Z standard in AvalancheGo for quite a while and been playing around with it internally. And I think that we see that the compression. So this is, to clarify, this is for P2P network compression. So this is the format that we send messages over the over the TCP connections between nodes, performing consensus, mempool gossip, things like that. And so by compressing the bytes, we're able to reduce the actual number of bytes that we send, which reduces bandwidth usage, which is reducing costs to the kind of end user and making it easier and cheaper for people to run nodes. So we compress all of our messages that we send over the wire, or at least most of them. And Z standard compared to gzip, which gzip was the previous compression format, is around 10 times cheaper to compress. And so the decompression time is around the same, and the actual compressed bytes is around the same, but the compression time, the time to compress the messages, is significantly cheaper. And so this is kind of just switching to a kind of newer and more or nicer compression protocol. So we switched that to the default, and so now all nodes running after 110.9 will use Z standard by default for all of the P2P stuff. And so we see as time goes on, basically the whole network will switch to Z standard. We'll probably end up deprecating gzip and removing it. There's really no reason for us to have it. Yeah, so that's kind of the namesake of the release. I also want to shout out that we added support for the C-chain import and export TXs to the Golang primary network wallet. So this has been maybe not as highly requested thing outside of the teams at Avalabs, but internally for a lot of managing of assets between, say, the C chain, the P chain, the X chain. This has been a really big pain point because the actual integration for C chain import exports of Avax has been pretty painful. So that landed in this release as well. So if anyone is using the AvalancheGo non-custodial wallet, so it's not inside of the AvalancheGo node, but just as a library, then it'll be a lot easier now to interact with the C chain using that primitive as well. So that's really nice and unblocks a lot of the stuff for Avalanche CLI.
One quick thing I want to just tie in there about the compression side of it. So as we talk about trying to reduce the amount of CPU used, and we're saying, the amount of bytes sent is the same. I think one of the interesting kind of balancing acts of compression is to say there's actually most of these algorithms for people that aren't familiar have a setting to say basically how aggressively you want to compress things. So if you're willing to sit there for a couple minutes, you can make this thing really, really compressed. And you may say, well, why don't you always just max compress things? Well, because it takes some of the CPU time away. So what you're trying to find is this interesting balance between what is an acceptable amount of CPU for a bytes savings or compression amount. And what we saw is like all else equal, right? With Z standard, the amount of CPU used goes down, dramatically, but continues to keep the same like compression quality, or compression efficiency is probably the word that's used, or something like that. And so this becomes even more prevalent in testing like more high throughput networks, because you're spending more and more time sending data over the network. And so you're often asked to make this trade-off, which is it better for me if I'm CPU bounded to actually not compress anything at all and just send the bytes directly because my network can handle it? Or do I want to take, 30, 40, 50 milliseconds per second to spend compressing if it means that I can reduce my bandwidth usage by like 50 or 60%? So on the mainnet, it makes a lot of sense, I think, to do this sort of compression, given like the existing topology of things. But on other networks, I think there's a more delicate game to be played around, like, maybe a lighter version of Z standard may make more sense, or even not having it at all. So I'm not sure if there's anything else you wanted to add to that sort of digression, but that's something that I was thinking about a lot when we were playing around with this.
Yeah, no, so I think one of the big things to know here is that Avalanche Go lets the user play around with this. So on the recipient side, Avalanche Go supports a number of different kind of compression modes. So currently it supports Z standard, obviously. It also gzip, but it also supports no compression. And we can definitely add new types of compression and play around with them as we go. So currently, any node, if they wanted to, could explicitly specify that they want to send gzip. You can measure that. You can specify there's no compression. So if you're explicitly making that CPU bandwidth trade-off on your side. And then you can also, if you get a little bit into the code, you can play around with the actual compression modes of either gzip or Z standard to actually further compress stuff if you really wanted to save on bandwidth. But yeah, I think for the most part, like Avalanche Go, if we don't have like a super, we aren't super opinionated on something, then we generally leave it as like as configurable as possible, for better or worse. If you look at Avalanche Go's config flags, it's a mile long, but some of those are more safe to change than others, by the way. Don't just go perusing and change things randomly. At least on mainnet. You can try it on Fuji.
Is there a middle out compression option yet, or is that still a work in progress?
I'm working on that. I'm still working on that. I've been rewatching a lot of shows, trying to read the whiteboards in the background. Anyways, but yeah. Anyways, going back to 110.9, I think that the last thing I wanted to mention here was that because all of the database migrations that we've been working through for 110.6 through 110.8, or probably even before 110.6, we were able to finally remove the optional height indexable VM interface, and so now all VMs are required to expose a height index. And so that means that all of the kind of consensus work that we have planned with height indexes is now essentially unblocked. So I think Josh, you probably have a PR from I don't even remember when, about your ring. What was it? The consistent hash.
Ring.
Consistent hash.
Yeah, we'll actually get that merged in now and start playing around with that stuff again. But yeah.
One of the big benefits, as a reminder, for like some of the site indexing stuff, we have a few different improvements planned, but one of the big ones is that you should now be able to actually concurrently fetch data from the network in terms of like actually blocks to Bootstrap. So one of the feedback we've gotten is like, obviously you want to minimize the amount of time it takes to Bootstrap without like DOSing the network itself. But right now we're very slowly kind of start from the tip and just go backwards one by one until we get all the way back. And this will let us actually like basically concurrently fetch ranges of blocks.
So one really cool thing, this is going to require some deeper changes to the consensus engine, so definitely not going to happen right away, but this will also make it possible to concurrently execute and fetch the blocks. And so currently the way it works is we fetch stuff from tip back to Genesis, and then we execute from Genesis to tip when we do a full bootstrap. And so obviously you can't execute something at tip if you don't know the state of the prior thing, and you can't know the state of the prior thing if you don't even have the prior block at all, right? So we do this kind of like fetching thing and then execute back. But with this height indexable thing, we can fetch at various points concurrently. And so while we're still, say, fetching something closer to tip, we may have already fetched a bunch of stuff at Genesis, so we could like execute that concurrently as we continue to fetch new stuff, which will be really nice because it switches from a IO bound, like basically waiting on networking and blocks, to be able to concurrently do like a disk bound, CPU bound process. And so now all of a sudden you can kind of really fully utilize your resources rather than like having these different resource constraints at different times. So I'm really excited about,
Assuming you even want to do a full bootstrap, that is.
I mean, I would never recommend doing a full bootstrap, but anyway, but if you have to, there's a number of people that have to for say like archival support and things like that. But yeah, as a validator, I would always recommend state sync, which is why we're going to try and add state sync to the P chain and X chain, which also requires height indexing. So another thing that's unblocked by all this. But anyways, a lot of improvements here.
Yeah, I think another thing that we chatted about was implementing like a distributed cache for bootstrapping as well, which we can do now that we have like height indexed blocks. So if we do that, we can actually have blocks being served as part of the bootstrapping APIs without even requiring reads from disk, and it can be served straight from memory. So we expect that should be a pretty cool optimization to implement as well.
The other thing that, not to spend too much time on Cortina 9 here, but the other thing that's really important here, kind of hidden between a few of these commit, is the changes to some of the MerkleDB locking. There's a number of different commits here. I don't know. If you search MerkleDB on the release page, you'll figure out something here. But the gist of it is, previously we had some less than coarse, or like less than fine grain or coarse locking, we'll say, on how some values could be fetched at different times, such that they would trigger root generation or just block in general. And that prevented us from doing a lot of this like deferred verification stuff that gets really interesting on a lot of different stuff. Or really interesting on like actually reducing the amount of time it takes to verify, and also better pipelining the use of resources in the VM at different times. And so that also was put into this release. So this was what, if you saw my thread on deferred verification, or like the deferred regeneration, that was unblocked by the Cortina 9 changes. So, but I think, since we have Josh here, I think we'll go now into the next topic, which is some coming up kind of gossip changes in some of the work we're doing to standardize the P2P library, which we call the P2P SDK. So Josh, I don't know if you want to share your screen, if you have anything you want to share, otherwise I can point to random stuff.
Yeah, I do. Let me figure out how to use this share screen thing. I see. Okay, yeah. Yeah, so I made some like small slideshow to talk about this. So yeah, I'm here to talk about some of the work we're doing, redesigning some of the transaction gossip that we're doing in the EVM. And this solution is more generalized such that other VMs can also take use of this. And in fact, it doesn't even need to be a transaction that's gossiped. The components that we're implementing are actually generic enough to gossip just an arbitrary like blob across like a network. But yeah, we can kind of go into kind of the details of the problem. So I guess like currently we have this transaction gossip implementation, which is kind of important because from users, like you issue a transaction to a node, and then the time between when your transaction is issued to when it's actually posted on chain, which is kind of like this end-to-end I guess transaction time, is defined from the time between when you issue the transaction, when it propagates across the network, when it lands onto a block producer, and then when that block producer actually produces the block. And so here with the current approach, we have this push-based algorithm where a node, once it gets a transaction issued to it, it will forward that transaction to a set of peers. So for the sake of this example, we're using like a gossip size of 1 to make this really simple. And so in the happy case, this works pretty well. Like 1 will gossip to 2, and this kind of just keeps going down the entire network. And then now the entire network has it, and so there's a 100% chance that it's going to get included into the next block, because one of these will be the block producer. It's going to get in, and then your transaction can be posted off the chain. This sounds great, but we kind of have a problem where we don't gossip it to a node that doesn't already know about it. So kind of if we rewind some time and we have node 2 gossip to gossip 3, if 3 sends it back to 2, this node won't forward the transaction anymore because it already knows about this transaction. So it kind of perceives this as a transaction that it already knows about, and so it doesn't need to gossip it again. And this is kind of important because we don't want to constantly re-gossip every single transaction all the time, because transactions are non-trivial in size. They can range from a few hundred bytes to a little over a kilobyte, I think, is most of the data that I've seen. And so if you don't have any kind of mechanism to kind of re-gossip old transactions, your gossip just stops. And this is bad because you could actually experience a transaction never being included on a chain in a very long amount of time, because gossip is sampled uniformly, whereas block production is sampled by stake. And so this is kind of the theory behind the problem that we see right now in the EVM gossip, I guess, end-to-end propagation delay. And so we ran some simulations, and we found that this is kind of in line with what the data looks like. So here on the x-axis, we've got the ith node that learns about the transaction, and the y-axis is time. And so we kind of see this exponential behavior where at first the transaction gets learned about really, really quickly, because the slope is really high. And then it starts getting lower and lower, and then it takes exponential amount of time more to kind of learn about this transaction. And this kind of makes sense going back to the previous slide where if we're only forwarding transactions that we don't know about, as more and more nodes learn about a transaction, they're obviously going to be less inclined to forward the transaction because more of the network learns about it, less nodes want to forward it, is kind of the problem we've got. So the solution we have is that we're going to do a pull-based gossip on top of this. So previously we were doing this re-gossip, which is effectively a periodic broadcast of just stale mempool transactions, which is obviously not the optimal solution because you may or may not be broadcasting transactions that your peers already know about. So with this pull-based approach, it's kind of like a request response protocol where a peer will periodically send a Bloom filter, which is just a probabilistic data structure describing set existence. So basically a Bloom filter is a summary of what is in my mempool. And so periodically each node will pull unknown transactions from its peers. So in this example, right, only one transaction or only one node knows about the transaction. So most of the nodes aren't going to get it yet. And so here 3 learns about it from 1. And then in the next iteration, roughly half the network knows about it. So there's a much higher chance that the transaction will be pushed across other nodes. And so now 2 and 5 know about it. And then finally 4 learns about it from 5. So this actually has the opposite properties as push-based, where previously we were only pushing transactions that we didn't already know about before. And so this kind of exponentially slows down. But with this approach, because we're always pulling unknown transactions, as more and more of the network learns about this transaction, it's actually more likely that you're going to get the transaction back on a response when you pull one of your peers. And so we expect this to be exponentially fast in terms of the transaction propagation velocity to the network. And in simulations that we run, we see kind of this expected result where as more and more of the network learns about this transaction, it builds this critical mass and speeds up more and more. So I think in the next upcoming release, we're expecting to use something like push and pull. Push being used to kind of build up a really quick mass of transactions immediately, and then this pull Bloom filter based approach to kind of get it over the finish line and finish up those higher quantile latencies. So it should be really quick at first, and then the pull based stuff should make it speed up exponentially fast to complete propagation of the rest of the network. And so this is like pretty exciting because these gossip components are being made as part of the P2P SDK. This SDK is kind of like a group of common components that people are using to build VMs. Like there's common abstractions like mempools, building like application handlers. Right now we've got support for building your own like router that handles like incoming app messages and sends them to the correct corresponding like app handler that you design. You can kind of think of it as kind of like HTTP like path-based like routing or something, if you're familiar with that. But we expect this to kind of like really simplify the developer experience when you're trying to make your own like custom VMs and build your own like custom like application protocols on a virtual machine. But yeah, that's pretty much all the slides that I've got for this right now.
Yeah, no, super cool. I am selfishly really excited to use some of this work with the IP gossip. So as far as Avalanche Go is concerned, most of the like the mempool stuff is left up to the VM because VMs have potentially different needs and requirements for mempools. But one place that we do a lot of this kind of gossip is with the IPs of validators to be able to connect to people. And so right now, if you actually look on mainnet for the bandwidth usage of message types, the peer list is actually quite high. And the reason for that is because we, from a consensus side, want to guarantee that nodes will always eventually connect to everyone that they're able to connect to. So doing that via a gossip mechanism can oftentimes be pretty complicated. But one of the things that I pretty much forced Josh to add to the P2P SDK was the like salt of the Bloom filter, so that nodes can locally define their own basically hash function for the entries being inserted into the Bloom filter, so that then we can guarantee that there aren't any like maliciously constructed IPs that will like mask other IPs in the gossip protocol given repeated rounds with different salts. So I'm really excited about that mechanism because you still get this property that you're guaranteed that you're eventually going to converge to everybody. But at the same time, you don't actually have to explicitly like send your peer lists to everybody. And so we should see a pretty great bandwidth reduction over time would be my expectation. We will still be sending these Bloom filters, and the Bloom filters are non-trivially sized, but the peer lists are also non-trivially sized because of the cryptographic proof of the IPs. So yeah, I'm really excited about that. Once we get the I think that this is all planned on being rolled out into 1.10.10. So hoping that once that gets out and we start being really happy with it, that we can start pulling that back into things like the IP gossip as well. So yeah, anyways, I'm super excited about it.
Yeah, I mean, I think the thing to note here for this mechanism is it's better for synchronizing state between different things. So instead of this notion of like trying to just push out what's needed to different people, it instead allows different people to like sync this, at least in the case of transactions, this pre-consensus information between each other relatively efficiently. And I think that makes sense for certain types of things that are meant to be longer lived. So for example, like the IP gossip, where like, the IP set usually is relatively consistent over time. So like fetching that via this mechanism is going to be much more efficient than just pushing randomly. Similarly with transactions in the EVM mempool, sometimes they sit around for quite a while before they're executed based on the fluctuations of price. But for different VMs, it may not make the most sense, especially like if there's like some sort of expiry or something like that, because by the time you actually finish like synchronizing everything, the transactions you're trying to execute could be expired. But I think that the point here is really just to provide all sorts of different tools that VMs could use for, random things like this. So, you could use it for like chunk syncing between different types of like, storage-based networks or all sorts of stuff, not necessarily just mempools. So yeah, cool. Anything else you wanted to add on that front?
No, I mean, I think it's like pretty cool. I think the SDK broadly is something I'm pretty excited about. There's a lot of like common patterns that you have to write, like figuring out how like a response maps to like a certain request or something that a lot of the SDK abstracts away. But yeah, I think it should make VMs like a lot simpler to be building.
Yeah, I think making sure that all of our kind of like gossip protocols have a push-pull mechanism going forward makes a lot of sense. There is one part of the consensus side that still doesn't use push-pull. So for the normal consensus protocol, when like a block is happening, you have basically pushes, which is the queries are kind of pushing information to people. And the chit that gets returned back in the querying process is actually a pull-based mechanism. So you get this kind of like really fast dissemination with the normal kind of querying process. But the one thing that doesn't work really well for is for non-validators. So you can actually see that if you're running a non-validator, sometimes you can fall a little bit behind tip before someone happens to gossip to you like, hey, that I accepted this like new thing. So it might make sense, and I know we've talked about this a bit, on changing our usage of the put messages for pushing of blocks to switch to use periodically pull get last accepted messages to kind of reduce the tail time to hear about new blocks through consensus. But yeah, anyways, we talked quite a bit about gossip, but yeah, I think that I don't know if we want to roll into the additional stuff in 1.10.10, which is the proposer VM header deletion. I don't know if that would.
I was actually going to give one quick shout out to something that we released that I realized we did not actually talk about at all. And that's the Oh My Warp site and thing. So last 2 weeks we had a lot of releases go out of all sorts of different stuff inside of the Avalanche ecosystem. And I'm not going to cover this too much in depth because Michael is going to join us in the next call to talk more about it. But I wanted to highlight it if you haven't seen it yet. And so this is just ohmywarp.com. And what this site is basically a interface to use warp messaging, or what we call teleporter, to move tokens, ERC20s, between 3 different subnets that have warp compatibility that are all EVM based. And so when people I often get asked, like, what is the most exciting, like, part you're most excited about for Avalanche in the next few months or years, or everything. And to me, it's like 2 things, which is like the massive growth of Elastic subnets, so people actually creating their own communities on top of Avalanche that are like self-sustaining ecosystems. And then the other one is actually the connectivity between subnets, and that's such a core part of having your own chain somewhere that the fact that it hasn't existed yet is a huge bummer. So hopefully what's coming soon will really make that easier and more impactful, but that is Teleporter. And so all the code is open on GitHub. So if you want to take a look at it, understand what's going on, we're still making a number of changes to it. But for a lot of people that haven't really experienced this notion of moving between subnets with like native Avalanche functionality, it's pretty eye-opening because of how quick it can be, a few seconds at most usually. So recommend checking it out if you haven't already, and we'll go into more detail of what actually is going on here next week or in 2 weeks with Michael. So yeah, just want to give that quick shout out. We'll go right now into the block pruning stuff. So let me pull that up now. I think I'll just pull up that PR, Stephen, and then you can kind of talk about it. All right. The quick question I see in the chat that I'll clarify. So what's teleporter versus AWM? So teleporter is actually like a mechanism running on top of warp messaging. So for people that aren't familiar, warp messaging is really just like this low-level, very basic protocol to move bytes between different subnets, authenticated bytes between different subnets. All it does is it says, hey, you want to move like this thing to another subnet? What we'll support is basically having the subnet validator sign that, create a multi-signature of their signatures, and then have a destination subnet verify it with the expectation that some percentage of stake has signed it on the source subnet. But all the part of connecting what those bytes are to the EVM in a way that makes sense for actually integration is teleporter. So teleporter is like a series of different contracts and different things like that that can be deployed on the EVM and precompiles of like warp messaging that can actually make it more useful to use. Because typically when you're using the EVM, you don't just want the bytes, you actually want like replay protection, you want all these different things in the EVM. There's actually a really good thread from Michael about some of this, and I'll paste it for the comments here while Steven starts to explain this topic. So Steven?
Sounds good. Yeah, so one of the interesting things about blockchains in general is that they're kind of this like ever-growing data structure, and people oftentimes really don't understand that design, just because in general, from a database perspective, you definitely never want something that just grows indefinitely. And so what people don't necessarily always understand is that actually validating a blockchain once you're synced up to tip, you don't actually need the historical blocks for anything. You need the current state, which the current state is just kind of the result of whatever applying your state transition function over all of your blocks up to that point, and kind of the last accepted block. So then when a new block comes in, you just apply that state transition on the prior state and you can move forward. So what that actually means in practice is that these old blocks aren't necessarily required. The only thing that they're required for is for full syncing a node. So full syncing a node means downloading all historical blocks and re-executing them, getting your current state. This is often useful for like archival nodes and things like that if you want to look up state at any given point in the history of the chain. But for validators, you don't really need that. So we added state sync probably around a year ago or so to the C chain. We're going to continue adding that to more chains and kind of make it the standard way for validators to join the network. But we didn't, until this point, really support block deletion correctly, or at least thoroughly. So this PR is to kind of fully unblock block deletion, which means that if a chain or if a node wants to be configured to not basically be able to support a full historical sync, so it won't help other nodes do a full historical sync of the network, then you can delete these blocks. Now, you do have to be careful if you're running a subnet and every node deletes the historical blocks. Well, you have just lost that information, right? So like you should be careful and have like at least some people that are performing this and have kind of the full historical state. But for just any given validator, it's not necessarily a requirement. So especially for a high performance blockchain. So Patrick has been doing a lot of work with the Hyper SDK to basically get as much throughput as possible through a chain. And so that means that we have, 2 megabyte blocks happening, what was it, every half second, every quarter second, Patrick?
It's configurable.
Anyways, if you're really pushing it, it can go really fast. So if you were to just be storing these 2 megabyte blocks, say every, second, just the block data, regardless of the actual state, ends up taking up a huge amount of space on disk. And so if you're really pushing a VM to its maximum limits, you desperately need to be able to delete your block data. And so this is explicitly adding support for that. Now, the one big kicker with this PR is the VM needs to be very careful not to delete blocks too aggressively. There are two careful edge cases here that the users should be aware of. One is if you delete blocks just like absolutely as aggressively as possible, you might not even be able to support state sync into your network, right? Because like people have to at least agree on like a recently accepted state. And so in order to do that, you have to have height indexing, you have to have blocks of like, at least a couple hundred blocks back to be able to like join in and keep up to date as new blocks are coming in. And then additionally, because the VM can actually write to a separate database than the AvalancheGo's database, you have to limit how different those views are actually on disk. So there can be like some subtleties with VMs around when they persist the actual acceptance of blocks and things like that. And if you get to a point where the proposer VM has deleted blocks that the inner VM hasn't actually persisted as accepted, and then you shut down and turn back on, then you can end up getting just a fatal error and you'll have to resync. So there isn't really a way to prevent that, and it's not really supposed to be prevented. It's kind of up to the VM designer to play within these bounds. In general, Avalanche VMs aren't like the owner of the VM can do anything, and when we say anything, we don't necessarily guarantee that it's smart, but that's so those basically are the two kind of major invariants to kind of keep in mind. But I think that this was the last thing inside of AvalancheGo that was blocking the Hyper SDK devnets. So I think that with this Patrick has been kind of really pushing to get some cool explorers and UXs for a Hyper SDK devnet. So I don't know if you want to talk about that. But
yeah, I mean, I just to reiterate the point about like block storage and how much of a burden it is on the VM. So, this is not the first virtual machine or framework to allow deletion of blocks, just to be clear. This is really more of a catch up on our side, frankly. But the simple math, and people may not think about this when they think about like high throughput, right? Let's just say that you're processing 25,000 transactions per second. Now, to be clear, that's more than any network is processing currently in production on mainnet right now. And it's not to say that like we will process that out of the box on like a super distributed network right away. But let's just say that that's your goal as a network to process that much throughput. Let's just say that each of those transactions is like 400 bytes each, which I think on the EVM, like the average like smart contract invocation is somewhere between like 300 and 400 bytes. In like a more minimal virtual machine, maybe you're going to get that down to like 200 bytes. Like I think a simple transfer on the Hyper SDK is like Morpheus VM is like 190 bytes or something like that. So it really depends on the complexity of the transaction you're describing. Like the basics though would be like the address is probably at least 32 bytes. And the signature is probably at least 32 bytes. So beyond that, like 64 byte minimum, like it's really up to you to depend on like how advanced you want that transaction to be. But let's just say that they're 400 bytes and you're processing 25,000 transactions per second. Well, that would mean that you need to store somehow 10 megabytes per second. And so out of band, you're like, well, okay, 10 megabytes per second. Like I know 10 megabytes. That's like, 1.5 songs on iTunes or whatever. At least that's how I used to think about it. And so you're like, oh, okay, well, like, few blocks of that, no problem. Maybe like 100 megabytes, whatever. Well, turns out that if you process 10 megabytes per second just of blocks, that would mean that you would need to store about 864 gigs of blocks per day. I think if my math is right. And so I need to check that math because now that I said that out loud, it doesn't sound right to me. Let me check that after I keep talking about this. But I was reading the README that I wrote the Hyper SDK. I'm like, that doesn't seem right. But like a lot of data, maybe 86 gigs per day. Nonetheless, it's a lot. And so if you wanted to like actually have a network that was processing consistently that much data, you got to figure out how to store that. And right now, like usually what would be done is just putting it on top of this like LSM database stored by block ID. And you're going to get very quickly into compaction hell of like having to maintain all this data on disk, not to mention the storage cost just grows like crazy as you do this. And so what was really the last goal for the DevNets was to have some way to maintain this so that really no matter how much throughput there was, we could bound it based on some number of blocks that you wanted to store on disk, and then really only have the storage or like disk usage grow based on the size of state. And so in the Hyper SDK, we ended up deciding to store around 768 of the last blocks. And that was decided really just to allow people to sync. Basically, if a node restarts, you don't want it to necessarily perform an entirely new state sync. And so if it restarts within, 700 blocks, it should just bootstrap up the tip that way instead of deleting all of its state and resyncing. This is also useful, like if you set your initial sync target during state sync. 768 blocks should be at least efficient enough for that. Now, that's, I would say, like the lower bound on what you'd want to store. Some people will store like a week or something like that, or maybe 2 weeks, and that's a configurable value, at least in the Hyper SDK, to set how much data you want to keep. But in the case of 2 megabyte blocks times 768, right, at max size, like you're talking about a couple gigabytes of block data versus unbounded growth. So it's much better, or really was the blocker for me to to really launch that DevNet. Let me do that math real quick.
I already did the math. You're good. 864 gigabytes per day. That's right. So at 10 megabytes per second, 800 gigs per day. Also, I'm surprised.
See, doesn't even sound right when I fucking do it again. Like it's so much data.
Anyways, going back though, so you said that if you were to fall more than 700 blocks behind, then you would have to wipe the state and do a resync. I don't think that should be true. It might currently be true in the sync package of the Merkle DB, but we can definitely do better than that. So, yeah, I can look into that.
So the number that was wrong is the terabytes per year. That's way off. I don't know how I got that number. It's probably like, closer to like 300 terabytes. Yeah. Sorry, what were you going to say?
That was it. So basically if you have a bunch of state on disk already, you can basically use the range proofs of new incoming data to like skip ahead. So like we shouldn't necessarily need to like do any deletion. But of course you will have to sync,
Yeah. I think like what I kind of have in mind here is like a lot of, I would imagine. So the whole point of this really is to say the node itself should not be the thing that's actually storing this block data, like the historical block data. You should really be exfilling that to like some more scalable database storage. Now, Pebble actually has this interesting feature where you can like use S3 as the backing store, which is kind of a nuts concept. And so we're going to play around with that to see if like we can have this like longer term block storage that just actually just shoves things to S3 and have it like kind of move into this other store. But you should not really probably store these on your disk. Like your disk should really be focused on just executing the absolutely minimum stuff required to execute the next block and to let people state sync to the network. But this buffer is really useful so that if you're actually processing like a block by block event, that when you restart your node, you don't just like accidentally skip some number of blocks. So I think that if you didn't care about that, I think that the state sync mechanism probably could be efficient enough. I think there's some improvements that have been shipped on the Merkle DB to like more quickly restart and like kind of take these things back via these change proofs. Sorry, I got to sneeze. All right. So I think that will help, but that's kind of what I had in mind here. Yeah, we originally thought that we could just store the latest accepted block, the processing tip, and Genesis. And I think we can get closer to that if we wanted to. But I was using some stuff in the Hyper SDK to allow you to like kind of determine where you would start your sync. And by bounding that, you kind of limit that. So I decided to make it a little bit bigger, although maybe it's not strictly minimal.
Yeah, I think technically, actually no, yeah, you probably do need it. Well, with the deferred root calculation, right? You don't actually need the parent block anymore, right?
Yeah. So there's a lot of stuff we've been down here behind the scenes. So one of the big changes was actually it's funny to bring up because it was really a relic of the Spaces VM and my very early designs, which is that previously we actually, at least the Hyper SDK, relied on the presence of the parent block to actually verify the next block. So it would pull the parent block from memory and then say like, oh, what was its gas price? What was it, unit price? What was all this stuff like that? And then it would actually inject that into the verification context. Well, under the optimistic assumption that we would not store anything other than the last accepted block, you can no longer assume that your parent is even going to be around for you to look at. So I migrated basically everything you would need to actually verify a block into state, and then relied on that exclusively. So yeah, the verification of a block requires no access to the parent. It just requires access to state, the current state, which I think is cool. But it definitely means you have to pull less, I think, from memory or from disk while you're in the verification loop, assuming that the block isn't in memory already or something. But much easier to deal with for like these kind of complex state sync scenarios for sure, knowing that everything you need is really just in the block itself.
Yeah, because I feel like you could probably get away with doing something clever with the state summary, where you only actually include the Merkle root and maybe the parent hash, rather than the full block in the state summary. So you might be able to get away with that.
Yeah. So right now, what Steven's referring to is kind of the way that our state sync mechanism actually works within the Hyper SDK, which is really when a block, like when a node first joins the network, how does it actually do that? Well, we basically ask the network or a sample of the network, like, what's your latest state? They then respond with that. And if we get, like a supermajority or majority of those responses that are the same, we'll then accept that block and then start syncing from there. But in the case that, at least the way I've currently defined it, the way that it works is you actually send really the whole entire last accepted block. You don't send just a sample or part of it. And so you can see like in the Hyper SDK, there's this like syncable block context, and really it's just the block, and then that can be called to be accepted in this like unique way that's particular to this. And so what Steven's suggesting is, well, you could probably get away from that and just send like some values from state, and that should be sufficient, I think, to actually initialize the chain. So
the reason that the reason that would be cool is because currently the inner VM only uses any block other than the last accepted block and any block prior to the proposer VM hard fork, which for new things is just Genesis block. Those are really the only things that are actually used via the VM interface. And so if you don't need those things internally, which currently I think they're only used for the state sync, and also any like batching out to like other indexers and things like that, then you could probably get away with having that block index at all, which would be pretty cool. But yeah.
Yeah, and so all this is in line of trying to create these like publicly accessible dev nets to start getting real measurements of like TPS and different scenarios and like really start to get feedback. And so what we're working on now that we have all these like kind of prerequisites complete, is some way for people to actually interact with the Hyper SDK. So I've been learning React, and I'm going to share my screen here. Very curious if this is going to work. Oh no, it's making me join. Shoot. Let me see if it lets me show this. Or it's going to make me quit. All right, it's worth showing. I'm going to be right back. Steven, hold down the fort.
All right, Patrick's gone. There's no rules. Josh, what do you want to do?
I think when he said he was like, yeah, React's really not that bad this morning, I just couldn't believe like my eyes when I saw that.
Nah, dude, this man is not a React developer. I can tell you that. Like,
I was surprised he got he has a website up and everything. Like the picture looked pretty good.
I think he's been getting a little bit of help from someone, but you never.
All right, can you see? All right, it works.
Okay,
all right.
Go.
So
hang on.
Check this shit
First
out.
question: did Connor help you at all with any?
This is all me.
Okay, wow.
Oh,
Fuck this. Like I've been putting off learning how to make a GUI for my entire life, and I finally decided, like, everyone fucking loves React. Like, I'm probably a decade late to the party, but better late than never. I'm gonna learn it. So I learned it. And turns out, like, for people that aren't aware, this probably sounds super stupid to anyone that already knows React, but there's a bunch of component libraries you can just rip and not actually have to know anything about design. So I don't know anything about design, and I just started ripping this component library that's maintained by like Ant Finance, I think. And I also didn't want to write any complicated TypeScript, so I used this tool called Wales, WAILS, which lets you more or less like skim Golang without actually like writing a web server or like anything. So this is like more or less an alternative to like an Electron app, but it actually is just running like compiled Golang as a binary and then exposing it to the UI. So like everything you see here is more or less just Golang functions wrapped in a very thin layer of React. And so the biggest thing I realized for the DevNet is like most people don't want to use a CLI, which surprises me, but is true. And so what I created, or what I'm working on creating, and there are 2 more tabs I'm going to add here, is basically a very simple wallet. And so it's going to have an explorer, it's going to have the ability to transfer, and it's going to have the ability to mint tokens, pretty much all in this single thing, and a faucet, so 4 tabs. And so what you'll be able to do when I hook this up is then, run whatever you want to run, and then test it out and like provide feedback, but it will be a long running, or at least moderately long running network. And so right now you see a bunch of 0 transaction blocks with latency. So now I'm going to just send a little load through this thing.
Is this on a local testnet or?
Yeah, this is on a local network. And so you'll see that very quickly, like everything comes alive, right? So you may say like, wow, like live refresh, he figured it out. Yeah, like I did all this, right? So like notice like the TPS is changing, like all the blocks are changing. Yeah, I think it's pretty cool. So I'm going to change all the stuff on the top to graphs, but long story short, very much focused on making the Hyper SDK accessible for people to play around with. I've been tweeting a lot about like these random technical changes, which I get excited about, but like really it's not going to be useful until people start to actually use it. And so the prerequisite to that is really just making it actually useful to use for anyone to just download. So that's how I kind of want to wrap it up, is to tease this, and it is definitely coming soon. So look, it is also, this is all open source. There's an open PR right now on the Hyper SDK repository. So if anyone wants to come in here and say like, wow, this is absolutely horrific front end code and you want to clean it up, more power to you. But the hope is that I'll provide a generic kind of like GUI framework for anyone launching their own Hyper VM to use that doesn't want to actually write all the TypeScript stuff. or like all the logic in TypeScript, because the cryptography is so flexible right now. Like I don't want to like have someone actually like implement an entire serialization library just to have it like be completely changed in a bit, which is easy to do in Golang and with Whales, but not super easy to do in like React or any of these things. So it's not safe for production use by any means, but it's really fun to play around with. So
Yeah, those costs for storage modifications are mooning right now.
Yeah, so I was hoping this would happen. So yeah, in this network, I purposely configured the targets very low, and so you can see here that the like in every block you can see the units consumed. So like bandwidth, you see I'm not actually creating any data. I'm just I'm just sending transfers between it, but I'm way above the target for the modification rate of storage, and as a result, the cost for that is mooning, as Stephen said. And so very quickly, this will mean that I'll stop issuing transactions because I can no longer afford them. But this is a very quick aside on the multi-dimensional fees, right? In this case, we're seeing that like the compute price is going up, the storage read cost is going up, but the modification cost is going crazy. So if you had transactions now that you were issuing that didn't actually perform any modification and were instead utilizing resources that were being, underutilized by the network, you could much more cheaply actually issue your transaction than you otherwise could if it was a single dimensional fee. But I'm really hoping a lot more of these like concepts that we've spent, what is now the last year working on, become much more tangible to people because it's, you can actually use it now. You can see it fly around. So all these are going to be charts on the top, and it's going to be way cooler. But that's the last thing I want to add. Yeah.
I wonder if we should. So I can see like the cost of like storage creation, right, is like significantly less than the cost of storage modification, and that kind of doesn't make sense, right? We might want to like. I feel like there is some interplay, right, between like.
It's all configurable. Yeah.
Yeah, that'll be interesting.
Yeah, I mean, I think this is not necessarily reflective of like what we'd actually expect to see on a live network, right? Like, we wouldn't expect the modification cost to be this, like 130 trillion times the cost of create. So, yeah, I think there's definitely tuning here, and this is the fun part, right? Is to say like, oh yeah, like I spent on my like this is all running locally, right? So you could just replicate everything I'm doing right now. And so the hope is that through like making it easier to run and getting, engagement with the community, like we'll understand like the things that don't make sense so we can start to actually tune. Yeah.
And I think so I was about to point out another cool thing is that it looks like you ran out of money, so it stopped issuing, and then the fees were starting to drop now because things were being underutilized, which is really cool. Anyways.
This is where the charts are going to be nuts.
Unreal.
Yeah, like the unit pricing thing. What I'm going to do is like have this like multi-line chart for the complexity, right, is going to be in this case for like the storage modify cost gets so big that everything just looks like zero, but it will be cool up until that point, which is a little stratification. I think we're out of time. We're about to be, so we'll wrap it up here. We did not get to talk about Avalanche-rs at all. We will talk about that next session with Yuho.
All right. Thank you, gentlemen. Wonderful conversation. Very enlightening. Not many questions. And as he mentioned, we are at time. So we shall be back on September 20th, and we will pick it up with Avalanche-rs and whatever exciting happens before then. Please check out Avalanche Developers, single word on Twitter. Oh, yeah. We'll very quickly just pass it around for last thoughts. Stephen, thoughts?
No, not really. Just having a good time. See you guys next time.
Josh, thoughts?
I mean, it was my first time in the community call. It's pretty fun. Hope to be here again. Really cool stuff going on in Hyper SDK and just SDKs in general.
Yeah, please join us again. And Pug, thoughts?
Yeah, excited to finally have like a demo the average person can use to see like kind of what you can do with the Hyper SDK. So I had to learn React for you, so just remember that. Yeah.
Yeah, the React wrapped around Go. That's pretty rad. I've never heard of that. All right, you guys, we shall be
You
back
can
on
clearly
September.
see my pain of trying to deal with front-end work. Okay.
Okay, everybody, we'll see you next time. Thank you for joining. Cheers.
Yep.